Well, thanks very much, Felix, and thanks very much to all the organizers for inviting me. I'm very pleased to be here. I did get in yesterday, so if I say something silly, please call me on it. It may be the jet lag. Also, please feel free to ask questions as I go along. I mean, this is a summer school. You're here to learn. I'm here to attempt to tell you a bit about astrophysical searches for dark matter. So yeah, please just ask if you have a question. Okay, so this morning Neil talked to you about the gravitational evidence for dark matter and a bit of how that constrains model building. So we heard that dark matter is cold, largely collisionless, and it's about 80% of the matter in the universe. Now, as those of you who work on dark matter already know, and as you'll see in Neil's later lectures, this still leaves a vast space of theoretical models consistent with those observations. As Neil said, there's a mass range from about 10 to the minus 20 eV up to the Planck scale in which particle dark matter could possibly live. So as a result of that, many of the searches that we want to do for dark matter nowadays focus on probing beyond the gravitational properties of dark matter and looking for its possible interactions with the standard model. So probing dark matter standard model interactions. Now, in particular, I was asked to talk about astrophysical and CMB searches. Now, astrophysical searches could cover gravitational probes as well, and I'll talk a little bit about those. But what I'm mostly going to focus on is what's generally called indirect searches for dark matter, which I'm going to define broadly to mean looking for the effects of standard model particles produced by DM physics, or the effects of those particles. So even if you can't see the particles themselves, you might be able to see the effects of them heating up the gas, modifying the propagation of cosmic rays, and so forth. So indirect searches, these are one of several probes of dark matter standard model interactions by setting limits on them. We can constrain models of dark matter. If we ever were to detect a convincing signal, it would give us a huge amount of information as to the nature of the dark matter and its interactions. Indirect searches, in particular, can probe a couple of questions that are largely inaccessible to other searches or are accessed much more indirectly through other searches, despite this being considered indirect. For example, the question of the stability of the dark matter. Neil showed those constraints that said the dark matter can't decay with a lifetime much longer than, can't decay with a lifetime much shorter than 10 times the age of the universe. You can do much better than that if the dark matter is decaying, either directly or indirectly, into anything even potentially observable. So you can address the question as, what is the lifetime of the DM? Does it decay? You are never going to see a dark matter particle decay in a collider experiment or a direct detection experiment, except in very special circumstances. But by looking for dark matter out there in the cosmos, we can try to probe this question. Also, in many models, the question of what standard model particles could be produced by dark matter collisions is intimately connected to the abundance of dark matter in the present day, that 80% of the matter in that 80% of the matter abundance in the universe. So these two questions and possible answers to these two questions drive two of the big classes of indirect dark matter searches, which is to look for the product of dark matter decay or the product of dark matter annihilation. So I have 4 lectures. So here is the plan as it currently stands. We'll see how much of this survives through the next couple of days. So the plan is, in this first lecture, I want to take you first through some back-of-the-envelope estimates for what we can detect through indirect searches. What kind of dark matter scenarios would we be sensitive to? In other words, I want to tell you, because if I want to tell you, how well can we do, and how does that motivate indirect searches? I want to talk a little bit about the scenario of thermal freeze-out. Which is not the only way, which is one possible answer to this question of how does dark matter achieve its observed abundance. It is far from the only possible answer, and Neil is going to talk more about other possibilities in his discussion of models. But this scenario provides an extremely convenient benchmark for dark matter indirect searches. And so I want to show you that so that you understand where a lot of these searches are coming from. And related to that, if we have something like this thermal scenario, then it immediately implies a host of effects of dark matter annihilation throughout cosmic history. So I want to talk a bit about that too. Okay. If we get through that, then in tomorrow's lecture, so this first lecture will be largely a big picture lecture. I'll be doing back of the envelope estimates. I'll be talking about this general thermal scenario and its general implications. In the second lecture, I want to go into a bit more practical detail about how you calculate signals from dark matter annihilation, about what the possible detection channels are and what you need to worry about. And I want to talk, and in that context, I want to talk a bit about cosmic ray physics, since looking for extra cosmic rays possibly originating from dark matter physics is an important possible direct detection channel. In lecture 3, so these first 2 lectures, I'll hopefully be teaching you the mechanics of how indirect detection searches work and how they're motivated. In lecture 3, which is the point at which we'll transition from mostly Blackboard to mostly slides, I want to tell you about the current status of indirect searches, where we stand, where we are. And if time permits, and 1, 2, and 3 haven't flowed into number 4, I want to work through a couple of detailed case studies of indirect searches that provide that are either just generally useful techniques or provide particularly strong bounds or relate to some of the anomalies that you may have heard about. Okay. So, that's the goal. Anyone have any questions about this? Okay, then if not, let's get to it. Okay, so this is what we want to talk about. We want to look for astrophysical searches for the standard model particles produced by dark matter physics or their effects. So this could be from decaying dark matter that is not absolutely stable, and decay is producing standard model particles. It could be due to dark matter annihilation, where 2 or more dark matter particles come together and produce visible particles. So the advantages of indirect detection is that there's a huge amount of dark matter density out there. It's 80% of the mass density of the universe. We don't need to make it. It's created for us. And we get to piggyback by looking for standard model particles produced in this huge amount of ambient dark matter. We can exploit the fact that we have a wide array of telescopes designed for astronomical purposes, which are pretty good at finding standard model particles incident on our detectors throughout the universe. And to the degree that gravitational probes can tell us where the dark matter is, we know where to look. We can pinpoint this, we can predict the spatial distribution of the signal. We can ask if a given potential signal looks consistent with where the dark matter is. Now there's a caveat to this, which is that there are regions where we don't know where the dark matter is very well, usually because there's a lot of baryonic matter there too, and it's hard to disentangle a subdominant dark matter component. So in those regions, this third point does not apply so strongly. So I suppose I'll pause at this point and just ask, can people at the back read my handwriting? Do I need to make it bigger? We're good? Okay. If it's not good, let me know. There's no point in me giving this lecture while you sit there for an hour and a half going, if you would just write in a slightly larger font size, this would be much more helpful, okay? Everybody good? Okay. All right, so these are all reasons that we might think, okay, indirect detection is potentially a useful probe, and it can give us answers to questions that we're not going to achieve any other way. But there are challenges to all of these astrophysical searches as well, which you should keep in mind. So the challenges are basically, but we know, as Neil said, the dark matter does not interact very well. We know from direct detection experiments and the fact that we have never seen a signal yet that it does not interact with standard model particles very well. You saw those constraints on millicharge and on the CMB. So dark matter standard model couplings are expected to be very small. So the signals that we're looking for tend to be rather faint, and there can also be large astrophysical backgrounds. In many channels. There are some channels where these can be mitigated. We'll talk more about those tomorrow. And this is not, none of these are lab experiments. We can't do a controlled experiment where we have the astrophysical background there and one where we don't. We can sometimes look sort of on-off regions to try to subtract off the background. But you'll see when we talk about dark matter physics at the LHC, or any new physics at the LHC, typically the situation is that the background is fairly well understood, and any 2 or 3 or 4 sigma excess above that background is interesting. What you'll see as we talk about this in more detail is that in dark matter, in direct searches, typically the background is not well understood, and any assessment of any 2 or 3 or 4 or 20 sigma excess that you might see, you need to think carefully about, is there some about what are the systematic uncertainties associated with getting the backgrounds or foregrounds right. Okay, but all that general stuff said, let's just do some simple back of the envelope estimates to figure out how well would dark matter have to be interacting with the standard model for us to be able to see something. Okay, suppose I've got some astrophysical object at some distance from the Earth. So this object could be a galaxy cluster. So distance capital R from the Earth. And it has mass capital M. Now, suppose I say that in some, suppose I want to say that that in this object, my dark matter particles are disappearing and converting their energy into standard model particles, either through decay or through collisions or some other process at some rate. so at some rate gamma. So if I'm looking at timescales that are much smaller than the inverse of this rate, then this rate times a time period will just give the fraction of the dark matter particles that produce standard model particles in this time period. So suppose I take a telescope at the Earth, and I want to know how many events does it see per unit time and per unit area of the telescope. What would this rate be? Well, so let's well, the area, so let me just write it as events per unit time first. So this object, which has mass m, so the number of total dark matter particles in this object is going to be the mass of the object divided by the mass of the dark matter. Okay? These produce standard model particles with a rate given by this rate. Okay? So this is number of dark matter particles, rate at which these dark matter standard model particles are produced. So this is the this is the rate of standard model particle production from the whole object. Now, how many of those particles do we see? So let's assume for the moment that we're dealing with photons. Well, actually, we don't even need to make that assumption, but let's assume we're dealing with photons and neutrinos. We just stream outwards at the speed of light. Or equivalently, let's just assume that this is a steady state system. So if we look, these particles move outwards. If we look at what fraction of the particles can be seen, it's going to be the area of our detector divided by the area of the sphere of radius capital R. Okay? So then if I want to make this events per unit time, per unit area of my detector, I'll just move this A out there. So this tells me that this rate, this observable rate, it's set by properties of the target object, mass over 4 pi r squared, and it's set by the rate divided by the dark matter mass. So this is a simplified version of what we'll later call the J factor, which just tells us about the astrophysics of the object. So this we can get from gravitational probes. And this term, which tells us about the dark matter model. So what's a sensible number for that astrophysical factor? That's going to tell us what kind of rates of dark matter destruction we can probe in an object like this. So let's, as an example, take the closest galaxy cluster to us. So the Virgo cluster, its distance from us is known. It's about 54 million light years, or about 16.5 megaparsecs, or about 5 times 10 to the 25 centimeters. If I ask what's the mass of the Virgo cluster, does anyone know roughly what the typical mass of galaxy clusters is?
10 to the 15 solar masses?
Yeah, it's normally like 10 to the 14, 10 to the 15 solar masses. Virgo is a pretty big one. It is indeed about 10 to the 15 solar masses. So if we can convert this into units, because I want to compare this to the dark matter mass. This is about 10 to the 72 GeV, if Google did not steer me wrong. So this is our rate here, our events per unit time, per unit area, becomes something like this. So all I've done here is take m 10 to the 72 GeV, divide by 10 times 25 times 10 to the 50. I come up with this number. So feel free to check this yourselves. So what's a reasonable size area for a telescope that we might be dealing with? Well, for sort of GeV to TeV gamma rays, The best instrument out there at the moment is the Fermi Gamma Ray Space Telescope, which has an area of about 1 square meter. So let's take, now you can potentially, with ground-based telescopes, you can get areas, effective areas that are 4 or 5 orders of magnitude higher than this. That's about as far as you can go. So let's take area about 1 square meter and an observation time of about 1 year. So these are, reasonable human-sized detectors and observation times that can be done within a student's PhD thesis. So if we take this and we ask, suppose we say, so then our events are going to be something like, so a year is approximately pi times 10 to the 7 seconds. So we plug this into here. We say, okay, we're going to multiply by 10 to the 7 seconds on this side. We're going to have our area be 10 to the 4 square centimeters. Then this gives us a total event rate, a total number of events that is something like this. So suppose in a detector like this, I wanted to see order 100 events for a detection. If I had no background, that would be 10 sigma. If you never see, have no background. So if I wanted 100 events, then this tells me that for GV to TV DM, I'm looking at rates here of something like 10 to the minus 26 to 10 to the minus 29 seconds. Okay, I can get down to 10 to the minus 29 seconds for GVDM. For TV dark matter, my number density is lower. I only know the mass density, not the number density. And so that would give me a rate like this. So if dark matter is decaying, this rate just corresponds to the decay rate for the dark matter. So this tells me that I would expect for GV to TV dark matter to be able to probe lifetimes in the order of 10 to the 26 to 10 to the 29 seconds for dark matter in this mass scale. Of course, this is very rough, but this gives you an idea of the order of magnitude. And that is actually about where the constraints from the Virgo cluster are. The current constraints in this mass range are about 10 to the 27 to 10 to the 28 seconds on the lifetime. So you'll recall that the age of the universe is about 10 billion years. This is about pi times 10 to the 17 seconds. So we're previously, by thinking, okay, let's suppose the dark matter is unstable, that changes its gravitational properties in the CMB, we could constrain lifetimes about a factor of 10 longer than the age of the universe, or lifetimes shorter than that bound. For decaying dark matter, if it's decaying into visible objects, and if this number, and if we had a telescope with this effective area and this observation time, and this was enough to see or rule out a signal, then you would expect to constrain lifetimes more than 1 billion times longer than the age of the universe. As it happens, so I'll show you these constraints in more detail in a couple of days, but for KV up to even exascale dark matter, you can set limits on the lifetime which are around the order of 10 to the 27 to 10 to the 28 seconds. So that's the power of indirect detection. We're getting a lot of this power from the fact that this ratio is really, really large. There's a lot of dark matter particles out there in any galaxy or galaxy cluster, and the fact that we can do observations like this is a function of the second point that we have sensitive telescopes. Okay. But you might ask, okay, great, we can constrain dark matter with lifetimes longer than, we can potentially constrain dark matter decaying with lifetimes 9 to 10 orders of magnitude longer than the age of the universe. How how might that connect to particle physics? Well, I'm not the person giving talks on dark matter models here, but I can give you some quick motivation for why these kinds of lifetimes might be interesting. Before I do that, anyone have any questions about this quick estimate? Does this make sense to everyone? Because we're going to do the significantly more complicated version of this over the next couple of days. So is everyone clear on what we did so far? Everything makes sense? Okay, good. If it doesn't, feel free to come ask me later, or of course just ask any questions. Okay, so what would we expect from particle physics? Well, as Neil told you, dark matter can have an enormous range of possible mass scales. There are an enormous range of possibilities for what the dark matter might be, but we can do a couple of illustrative examples. So, in general, we want the dark matter to be near stable. So, that usually means that there has to be at least some low-scale apparent symmetry that keeps it stable. Yeah?
Sorry, I don't understand how you get from such a weak constraint on dark matter lifetime 10 to the minus 26 seconds up to such a very, very large constraint on the dark matter lifetime.
10 to the 26 seconds.
That's what 10 to the minus.
Yeah, that's a rate. Sorry, inverse seconds.
Yeah.
Sorry. Yes, no, good catch. That should be inverse seconds, not seconds. This is important. This is an important distinction. Yeah, what I'm talking about here is a rate. So it's the inverse of the lifetime. No, thank you for the clarification. It's important to get where the units are themselves or themselves to the minus one. Okay, so if dark matter is close to stable, we often require some symmetry to keep it that way. But, so the classic example of this is that in supersymmetry, it's R parity that stabilizes the lightest neutralino and also incidentally prevents protons from decaying, that being a good thing. But this can often be a more generic feature just because if you want the dark matter to not decay into anything, often the way to do that is to introduce some symmetry that keeps it stable. But that symmetry doesn't necessarily have to be an exact symmetry of the full theory. Could be broken by higher dimensional operators. There could be some high scale physics that breaks the symmetry. So suppose, for example, suppose we had order TV dark matter. I'll show you in a moment why we might like order TV dark matter, but this is a characteristic scale that naturally gives you the right dark matter abundance. And the symmetry that keeps it stable is broken at some high scale, and arbitrarily I'm going to choose that high scale to be the gut scale. It's a high scale that we know is there. There could reasonably be some new physics there. Okay, so what are the options for this? So what are the possible rates for this higher dimensional operator? Well, we can just classify these by the dimension of the operator. So for example, if this is a dimension 5 operator, the natural time scale is 1 over MTM the natural time scale is this. The effect of coupling is suppressed by a power of m gut. Cross sections and rates are suppressed by a power of m gut squared. It's equivalent, so the rate is suppressed by a factor of m gut squared. The lifetime is enhanced by a factor of m gut squared. So if we take these numbers, if we take order TGV dark matter and put in the gut scale, so we get the gut scale squared over a TV cubed. If you put this in and convert GV to seconds, note that 1 inverse GeV is about 6 times 10 to the minus 25 seconds, you find that this is about 1 second. So that's not going to do it. If you've got any kind of dimension 5 operator at the gut scale in your theory, this is not going to be the dark matter. Okay? This is bad. This is not dark matter.
Can you explain again how you wrote down the first equality?
Okay, so right. Well, so yeah, I should put a tilde here because of course, I mean there will be couplings, there can be factors of 2, etc. So all I'm really saying is that
You mean like the powers of each
yeah,
mass?
yeah. So right, so roughly speaking, imagine I've got an operator in the Lagrangian, which. So imagine that I have an operator in, well, yeah. See, I've got an operator in the Lagrangian which couples my decaying particle, whatever it is, I'll call it phi, to the other stuff that it decays into. I'll call that collectively some final state F. This is not going to be just one particle, okay? There'll be some other stuff. So if I say that it's a dimension 5 operator, so this is overall dimension 5, so I need to have some high scale in here, right? Just to get the dimensions right. This high scale, I am guessing, in this case, is MGUT, okay? That's what I mean when I say it's a gut suppressed operator. This doesn't have to be the case. It could be some other high scale of new physics. This is just for the example where it's some new physics at the high scale. Okay, so I've got this effective operator. Maybe, you know, I've got some decay path like this. I've got an effective, and you know, there may be some G's, there may be some various couplings in here, but I've got an effective coupling here which goes like this in the diagram, in the amplitude, okay? So the high scale dependence in the result is going to be the square of the matrix element, so it's going to be 1 over the high scale squared, okay? But I know the dimension of this thing, right? I mean, I know that my rate has to have an overall dimension of mass. The other math scale in this problem, this is, yeah, so there's another assumption here, which is the only other important mass scale. The only important mass scales in this problem are the suppression scale and the mass of the dark matter. So if that's the case, then just to get the dimension right, has to look like this, okay? And then tau, well, actually, that is an equality. Lifetime is this rate to the minus 1, so that gives you mgut squared. Okay? Similarly, for the dimension 6 case, where we have an operator that we're saying is suppressed by 1 over this high scale squared. Okay? So that tells me that my rate is going to go like 1 over this high scale to the 4th, and then to get the dimensions right, I'm going to have something that looks like this. So that tells us that tau, if we approximate tau, and again, put in the same numbers, then what you'll find when you do this is that this comes out as about 10 to the 26 seconds. So this is a reasonable dark matter candidate. So
One question.
yeah.
With dimension 5 operator, what is the mass dimension of F and phi again?
Okay, yeah, so, right, so, well, so, okay, so if I want this to be a dim 5 operator, so for, yeah, so, right, so like, I mean, it can be any, so, well, if this has dimension 1, it can be anything, it can be any sum of things that has dimension 4, right? So, I mean, like, so this could be a 3-body decay to a vector and 2 fermions. It could be, I mean, it could be a collection of other stuff. Okay, I'm just saying that if there is a higher dimension operator that exists with this dimension, yeah, so sure. So F is collection of fields such that dim phi plus components of F equals 5. I mean, it doesn't, I mean, this is just a rough estimate. In a specific theory for what's going on at the high scale, I can predict, okay, how would this particle decay away? But if this is a dimension 5 collection of objects, then the mass dimension of this coupling has to be 1 over m. And so you get this scaling. Does that make sense? I'll give you an example of a long lifetime decay where I explicitly write down all the what everything in the final state is in a moment. The point I wanted to make here is just that given that you're probably imposing some low scale symmetry anyway to get the dark matter close to stable, you already know that there's no tree level process that lets the dark matter decay, and that even higher dimension operators that allow the dark matter decay may need to be absent or highly suppressed. If you were just to take back of the envelope numbers for a dark matter particle roughly around the weak scale that was decaying through some high scale physics, then these kinds of numbers, around 10 orders of magnitude longer than the lifetime of the universe, are the sort of numbers that you might expect to get. There's another, if you want to look at a specific example from particle physics, there's a very classic dark matter candidate, which is that it's some kind of sterile neutrino. So if the dark matter is some sterile neutrino, then it has some small mixing with ordinary neutrinos, but doesn't itself interact through the standard model weak interactions. So anything that an ordinary neutrino can do, so can the sterile neutrino, but with a much smaller rate determined by this mixing angle. So, for example, and if it's the dark matter, as Neil said, fermionic dark matter needs to be heavier than about 200 eV in order to make dwarf galaxies. So for dark matter, we usually think about a roughly keV scale or several keV scale sterile neutrino. Now, if you have if you have this particle, you might ask, okay, well, how can it decay? So the dominant radius of decay for the sterile neutrino is that, so I'm going to call this neutrino 2. It comes in, it mixes with the standard model neutrino. And then because the standard model neutrino does interact weakly, I can get a diagram like this. Okay, where this is the lepton corresponding to the neutrino. This is just the standard model W boson, and this gives me a radius of decay of this standard model neutrino, of this sterile neutrino into a standard model neutrino plus a photon. Or you can put the lepton on this leg and the W on this leg as well, instead. It does not really matter that much. Okay, so here's an example of so if this mixing is small enough, this decay is already loop level, the lifetime for this decay can be extremely long. So the lifetime for this decay So there's a recent review of sterile neutrino dark matter by Kev Abazagian, which has this expression in it, among several others. So here, theta here is the mixing angle between the sterile neutrino and the standard model neutrino. So this is like a measure of to what degree is the sterile neutrino actually standard model neutrino. So here ms is the mass of the sterile neutrino. And if the sterile neutrino is indeed down around the keV scale, then it's too light to decay into electrons or positrons. The only standard model particles it can possibly decay into are photons and neutrinos. So this channel is actually one of the leading ways to look for sterile neutrinos, and there's in fact an existing anomaly at about 3.5 keV photons that there's been a lot of discussion about because of the possibility that it could be this kind of decay signal. So again, you see that this has a pretty strong scaling with dark matter mass, but if you're down, but the 3.5 keV line, which we'll talk about a bit more later, is a signal that looks like, if it's coming from a sterile neutrino, it would be a 7 keV sterile neutrino decaying with a lifetime of around 10 to the 28 seconds, which is again in that ballpark that we forecast you should be able to see. Although the forecast that we did before was for GeV to TeV dark matter, and this is much lighter. But actually, it turns out that you end up having similar sensitivity to decay rates across a much wider range than the range I worked them out for. This is partly just a factor of, this is partly just a coincidence. It's a statement about how good the telescopes are and how long they observe for as you go down to different energies. But anyway, so the point of these slides is essentially just to tell you that in particle physics models, it is not that difficult once you've imposed that you have a nearly stable object already to have decay rates that are down at this highly suppressed rate about 10 orders of magnitude longer than the age of the universe. And fortuitously for us, decay rates like this are actually very detectable using telescopes that can be built with roughly human length scales and non-roughly human time scales. Yeah?
Yes, do we assume some kind of scattering for this missing angle? Because we easily could think that this new one could also turn into the sterile neutrino via mixing.
The new one the new one can go back to the sterile neutrino as well.
It's just a mixing between
Yeah, so that's true. I mean, remember that in this picture, the sterile neutrino is much, much heavier than the, it's much heavier than the light neutrino. So, I mean, you will have, you could look for signals of like sterile neutrino scattering in the early universe, but at late times, this thing is a keV. There are no neutrinos that have anywhere close to enough energy to scatter and make sterile neutrinos at late times. Does that answer your question, or were you asking something slightly different? Okay. So does it answer your question, or were you asking something slightly cool?
You have to think about the equation for the mixing angle, because there's this probability they can calculate how transition works, but I don't quite remember.
That's right. So you can get constraints on sterile neutrinos from things like neutrino disappearance experiments, like what's the possibility that the neutrino turned into something else that we couldn't see along its trajectory. Those are mostly constraining much lighter sterile neutrinos, like sterile neutrinos down at the EV scale, not at the keV scale. Because you get a suppression based on how off-shell the sterile neutrino would be too. And it's pretty off-shell. Okay. So until next time, that's what I mostly want to say about decaying dark matter. But I just want you to remember this one thing, that the kind of scales that we can constrain, that the kind of lifetimes we can constrain correspond to lifetimes sort of 10-ish, 10 to 13-ish orders of magnitude longer than the age of the universe. Because that will, so in other words, that corresponds to 1 in 10 billion dark matter particles has decayed over the age of the universe. Okay? This is going to come up again. That's about what we can constrain with present day experiments. Okay, so let me now talk about the other question that I brought up at the beginning about what determines the DM abundance. Now, there are a lot of possible answers to this question. Yeah?
Sorry,
Yeah.
on this age of the universe, but how many factors above the age of the universe does it have to be that they're actually like do the rest of the stuff that you want dark matter to do. So like, I could sort of imagine that you fairly overproduce dark matter in the early universe and have some of it decay on order lifetime in the universe.
That's hard, yeah, so that's really hard. So the constraint that Neil showed at the end of his talk, which is basically just saying if you had dark matter, a meaningful amount of dark matter decaying away during the lifetime, like during the epoch after the CMB, or during and after the CMB, then how much would that change the CMB spectrum? Not from purely, regardless of what the dark matter decays into, just from having the dark matter removed from the picture. And he said that based on those purely gravitational constraints, dark matter has, well, if it's 100% of the dark matter that's decaying, it has to have a lifetime more than about a factor of 10 longer than the age of the universe. Okay, so the kinds of lifetimes that we're talking about here will have pretty much no gravitational effects. I mean, this is 1 in 10, but so we can measure the amount of dark matter in the universe from the CMB at an accuracy of a couple of %. So if 1 in 10 billion dark matter particles decays, these sorts of the decays will have essentially no effect on the gravitational behavior of dark matter. Now, when we talk about annihilation, which we'll do so next, we'll see, just giving you a preview, that actually the kind of annihilation rates that we can constrain, maybe not surprisingly, correspond to about the same fraction of dark matter in the halo annihilating over cosmic time. So again, it's like 1 dark matter particle in 10 billion in our galactic halo would annihilate over the age of the universe for the kinds of annihilation cross sections that A, we can see, and that B, are motivated by the WIMP miracle. But in the case of annihilation, if you have regions of particularly high dark matter density, the annihilation rate can be greatly enhanced in those regions. And so there are circumstances where the annihilation rate can be important in depleting a significant fraction of the dark matter in an area. Even if in our galaxy only 1 in 10 billion dark matter particles has ever annihilated. But for decay, you can't really play that game. I mean, the decay rate is not typically affected by the amount of dark matter that you have around or by other properties of the environment. It's just the lifetime. So yeah, so if you can say this, and for a fairly wide range of dark matter masses, we now can say this, that if it decays at all, it's with a lifetime more than 10 orders of magnitude longer than the age of the universe, then that essentially tells you there are not going to be any cosmological constraints. But they're complementary because these sorts of searches assume that at some point you get standard model particles out. I mean, it doesn't have to be a direct decay. It could be you decay to something else which at a later time decays back to standard model particles, but you have to get a standard model particle or you won't see a signal. Whereas the constraints that are factor of 10 longer than the age of the universe are assuming you could decay into something completely invisible that you will never see in any telescope. I should also mention, for decay purely in neutrinos, the constraints are a few orders of magnitude weaker than what I've said here, just because 1 square meter and 1 year of observation time effective area is fine for a photon telescope. If you have neutrinos, you do not see the vast majority of the neutrinos that come through, so you need to put in a factor for that as well, which is how many of the neutrinos that hit your detector actually give you a signal, and that drops it by a few orders of magnitude. Okay, so I've just argued to you, in fact, that what determines the dark matter abundance is probably not dark matter decays. You know, that if you're decaying into standard model particles, that the effect on the abundance of dark matter at early times or the late times is probably pretty negligible. But it can often be true that the dark matter abundance is controlled by its couplings to the standard model. This is not a universal. There are cases like the axion where the dark matter abundance is essentially just an initial condition, but in many models, the DM abundance is set to the standard model. In the axion case, you're effectively in the limit where the coupling to the standard model goes to 0 for these purposes. And so your abundance is mostly set by an initial condition instead. In particular, in what we call the thermal relic scenario, the relic abundance is entirely determined by the annihilation rate of dark matter particles to standard model particles. So by relic abundance here, I mean the abundance of dark matter at late times. It's the abundance that we measure in the CMB. Okay. So decaying dark matter is the case where even if I have just one dark matter particle in the initial state, a reaction can still happen. I can produce other particles in the final state. So we can just go up from there and consider annihilation, which is I have two dark matter particles in the initial state. So annihilation, which in its simplest form is two dark matter particles go to other stuff. So ideally, for our purposes, standard model particles, but it could be some other, it could be dark sector particle or some other new particles. So a process like this is not typically forbidden by whatever symmetry keeps the dark matter stable, if there is such a symmetry. So this, unlike decay, can often occur at tree level without being a problem. For example, in supersymmetry, a frequent scenario is that the dark matter is a gaugino. For example, it's the lightest supersymmetric particle. If it's a gaugino, you might have, so for example, for the Wino, which is the superpartner of the W boson, you can have a process where through the T-channel exchange of a chargino, you can annihilate into W bosons. Now, this is for, so Majorana is its own antiparticle. So it can self-annihilate. In the case of direct dark matter, instead, the interaction that you're looking at is dark matter plus anti-dark matter goes to some final state. So the rate, so this is a two-body process, so it scales, so it requires two dark matter particles, so its overall rate scales like the dark matter density squared. And that rate is described by the cross-section, as Neil wrote down. So the rate of annihilations per unit volume per unit time is going to go like the cross-section times the number flux of incident particles. So if we were dealing with distinguishable particles, then this rate would be like the cross-section times the number flux of particles of type 1, incident on a target composed of particles of type 2. So this is the relevant rate for, say, Dirac dark matter. If we have instead indistinguishable particles, then the rate is instead sigma times VREL times n squared over 2. So here n1. Here these are number densities. and N in the case where there's just one species. This word is indistinguishable. Sorry that it trails off at the end here. Just making a bit so the reason for the factor of 2 here is just to avoid double counting pairs of particles. It's just like the fact that if you take a collection of n particles, the number of pairs of identical particles are n times m minus 1 over 2, not just m1 times m2. I just mentioned this because this is a factor of 2 that comes up in converting results for Dirac dark matter to Majorana dark matter. So it's worth keeping in mind. So I want to know, all right, if this process is active in the early universe, it can deplete dark matter particles and produce standard model particles. But in the if this process exists, it can also go the other way. I can have the standard model particles that appear in the final state here come together and produce the dark matter particles. So the thermal freeze-out scenario hypothesizes that this process is entirely responsible for setting the dark matter abundance through depletion of an initial abundance of dark matter particles. So let's consider. So Neil, you talked a bit about the Boltzmann equation in the early universe, I think, in the cosmology section of the class last week. So in the presence of this annihilation process, let's consider the evolution of the GM number density in the early universe. With no annihilation, we know how this process works. It's just that the number of dark matter particles is conserved, so the number density of dark matter particles times the comoving volume doesn't change over time. So we can expand this out and get this result, or dividing out by a cubed on both sides. And this a dot on a is, of course, just what we call the Hubble parameter h. Now, once we turn on annihilation, the rate of dark matter particles is going to, the number density of dark matter particles is going to have an additional contribution. So if it's, as I wrote here, two-body annihilation into standard model particles, going to have the same expression on the left-hand side, so this corresponds to just the dilution of the dark matter density, number density by Hubble expansion. But then we're also going to get a term. We'll do this for identical particles, but it should be pretty straightforward for you to convert from identical particles back to non-identical particles. The brackets here indicate that I'm going to take a thermal average, so I'm going to take an average over this sigma times the relative velocity of the particles. Since they're all moving around, they won't all have the same relative velocity. But each such process like this, where two dark matter particles come together, this is the rate of annihilations per volume per time. Each annihilation is going to remove two dark matter particles, in this case where they're identical. So I'm going to have a term like this. So this tells me about the depletion of the dark matter density. But I'm also going to have another term which comes from the reverse process. So all I know about this process is that it's not going to be dependent on the dark matter density, it's just going to be an n-independent term from whatever processes produce dark matter. So, okay, but I can write this in a simple way, because in the case where the dark matter is in thermal equilibrium, where all what this annihilation process is doing is just in the case where this annihilation rate is very, very fast, the effect is going to be to keep the dark matter in thermal equilibrium with whatever it's annihilating to. Okay? As Neil said, if they're in thermal equilibrium, then that tells you immediately what the dark matter number density is. So what I want is that if this factor is large, then everything on the right-hand side of the equation should force n to be equal to its equilibrium value. So from that, I can deduce that the correct result is going to be okay, and that's just obtained by saying, well, I know that the first term, the term that depends on n, has this cross-section sigma v. And I know that I want the effect of this right-hand side of the equation to be when I make this prefactor very, very large, then I want n to be forced to n ec. This will n equilibrium. So this term has the effect of doing this. When I make this very, very large to satisfy the differential equation, this term in square brackets has to be small. So, okay, so this is our Boltzmann equation for evolution of a species coupled by two-body annihilation to the standard model thermal bath. And as Neil said earlier, this equilibrium value has two broad regimes. There's a regime where it's just scaling like the temperature cubed, when the temperature of the universe is much larger than the dark matter mass. And there's a regime where it's exponentially suppressed when the temperature of the universe is much less than the dark matter mass. And there's a bit in between where it's a little more complicated, but we won't have to consider that. So we have two regimes. So we have two regimes in the evolution of this equation. The first regime is where so when this prefactor, this annihilation rate, is sufficiently large, n is forced to its equilibrium value. As this prefactor goes to 0, we just recover the usual scaling that the dark matter density is just diluted with the expansion of the universe. So the intermediate regime, the crossover, comes when this term here, this 3hn term, is comparable in size to these terms on the right-hand side. So So what we expect to see if we look at the evolution of the number density is that it follows. So you can see here, so let's cancel out the ends here. So when the number density of the dark matter is large enough, so this side is much larger, we expect, so let's make this a time coordinate, and this is the number density of the dark matter. So while this quality holds, we expect n to follow its equilibrium value. So its equilibrium value is going to be, actually, yeah, let's make this t instead. So then NDM is going to scale like t, let's make it 1 over t, so that as we go to the right, we have increasing time. So then the number density of dark matter is going to fall off like 1 over t cubed. In fact, okay, I'm going to do one more thing. I'm going to write this as NDM divided by t cubed. So in the regime where t approximately scales like, where t scales like 1 over a, this is like NDM times a cubed, so this should be roughly constant with respect to time. I'm going to ignore differences in the effective degrees of freedom. But then roughly we would expect this abundance to be in equilibrium, we would expect this abundance to be fairly constant, and then to start to fall off exponentially below once the dark matter becomes non-relativistic, once the temperature drops below NTM. Now, what this tells us is that what we would expect is that we should follow this trajectory, that while this condition is satisfied and will largely follow its equilibrium value, then when this condition is no longer satisfied, it will diverge from the equilibrium value and start just scaling like a to the minus 3 again. And depending on the strength of this cross-section, that final value might be here, or here, or here. So let's just consider, so for the full solution to this equation, you can work out this equation numerically. You need to relate the temperature to the expansion history of the universe using the number of effective degrees of freedom. But what I'm going to do now is just treat this equation in a very approximate way so you can see roughly how this is going to pan out. So let's consider two cases here. The first is a hot relic where this condition is satisfied at a time that the dark matter is still, at the time that the temperature of the universe is still much larger than the dark matter. So this is the first line here. This freeze out happens while the dark matter being in thermal equilibrium still just means that the number density of the dark matter scales like t cubed. Well, if that's the case, then what this tells us is that n, so at, okay, then what this tells us is that when this freeze out occurs, if this is true, so up until the time that this is true, n will closely trace its equilibrium value. So we call this time freeze out, i.e. sigma Vn is approximately equal to h. N is also approximately equal to its equilibrium value. So we can just try to solve for so in the hot relic case, we have n as approximately t cubed. If we're still in the radiation dominated epoch, so then this tells us that I'm going to say this. So this tells us that the equilibrium value, how do I want to say this? Okay. So this tells that n equivalent times t cubed goes like this result. This tells us that n equilibrium evaluated at freeze out times the scale factor at freeze out cubed is just the temperature of freeze out cubed times the scale factor at freeze out cubed. Now we know that n at much later times after freeze out is just going to scale as 1 over a cubed, approximately just by its ordinary dilution. So we know, but furthermore, we know that this ratio of scale factors scales pretty much just like the temperature. So in this case, what you expect is that the number density. So in this case, what you expect is the number density of the dark matter has always just been scaling like 1 over a cubed. It keeps scaling like 1 over a cubed forever. It just scales like the CMB temperature. So in this case, the number density of the dark matter is always comparable to that of a radiation species at all times. So that tells us that the number density of dark matter in this case should be approximately equal to the number density of photons. Now I'm leaving out things here like the change in effective degrees of freedom. I've said here that T is proportional to 1 over A, which is not true when the number of degrees of freedom is changing. But as Neil said earlier, in the standard model, the number of degrees of freedom does not change that drastically. It changes from above 100 at very early times before the electroweak phase transition down to 3. Down to, well, I guess it depends when you count it, but down to effectively 3 in the present day. So while you can put in these G star factors, the number density of dark matter being equal to the number density of photons is a pretty bad prediction unless the dark matter is very light indeed. And at that point, it would be well below a keV. It would be hot dark matter. You can see this just by saying the baryon to photon number ratio is roughly 1 billion. If we know that dark matter that was once in equilibrium with the standard model, which has to be warm, has to be more than a keV, well, okay, if it's got 1 billion times the number density of baryons, and if it's got a keV mass, then that means that there's a lot more energy in this than just 5 times the baryon number density. So this is bad. So the hot relic scenario leads to very light, hot, dark matter. So this, so the only way in which this can work is, that I know of, there may be another, you may come up with another trick, unless there is a very large change in number of degrees of freedom. In the early universe. So if in the very early universe, instead of having 100 standard model degrees of freedom, we had thousands or tens of thousands of degrees of freedom, the dark matter decoupled, and then those degrees of freedom heated up the standard model bath, then possibly you can dilute this dark matter enough to get a workable model. But setting that aside, let's look at the other case, which seems more promising, since we know that the dark matter is fairly cold. Okay, so in the cold relic case, we're going to still use this same criterion, but now the thermal relic that we put in, the equilibrium abundance that we put in is going to be that appropriate for a non-relativistic particle. So our freeze-out condition is going to become sigma v. So this is now going to give us so this is going to be our new freeze-out condition, and what we want to know is what is the value of n equilibrium as a function of sigma v. So what is this flat plateau level that will set the late time density of dark matter? Okay, so I'm going to do this in the quickest way I know how, but I'm also going to introduce a little bit more generality because I think it'll be useful. Suppose that instead of just having two-body annihilation, I could also consider processes where there's more than two dark matter particles involved that's dominating the process. So by this I mean the n dark matter particles collide and produce a final state which is either a standard model particle or at least in equilibrium with standard model. Then my rate here, instead of just being sigma v times 1 power of n, essentially all that's going to change here is that I pick up extra powers of n equilibrium, and then I need to replace sigma v with more powers of the relative velocity, because now I need to care about the relative velocities between the multiple particles in this collision. So schematically, what the Boltzmann equation looks like in this case is this. And our freeze-out criterion so the F subscript here is just denoted, I'm just going to use to denote quantities that freeze out. Okay, so for the capital N equals, it's a capital N, lowercase n means number density, so the capital N equals 2k, this just comes back to the relation that we had before. So, I'm now going to proceed to make a bunch of approximations. And there may be there may be combinatoric factors in here, depending on how many of these particles are identical and how many are not. But they're going to be order 1, so I'm going to ignore them. That is the first of many order 1 factors which I'm about to ignore. Okay, so we know, so this is our condition. This is our condition for freeze out. And in fact, so the other thing that I'm going to take from this is, so if this criterion is not satisfied before freeze out, once freeze out begins, once the temperature of the universe starts dropping below the mass of the dark matter, so if this criterion was not satisfied when the temperature of the universe is higher than the mass of the dark matter, that means that this term on the left was originally larger than h, but once the temperature of the universe starts dropping below the mass of the dark matter, this left-hand side of the equation is going to be exponentially suppressed and will drop very rapidly. So it's reasonable to approximate that the temperature at which this equality holds is going to be somewhere close to m. It actually turns out is often about a factor of 20 below n, but so at this point this e to the minus factor is e to the minus 20. So it's not going to be thousands or millions higher than h, because then the left-hand side of this equation would have a suppression by e to the minus 1,000 or e to the minus 1,000,000. Okay, so the approximation that I'm going to make here is that the temperature of freeze out is going to be approximately the mass of the dark matter. As I said, the real answer is that it's usually about a factor of 20 below the mass of the dark matter. So keep in mind that we're throwing away order 20 factors here, but so long as we don't throw them away in the exponential, this will be okay. Okay, but if we know this, what we want to know if we want to predict the late time abundance of dark matter is just this number density of dark matter at freeze out. Because once we have that, we know how it evolves in the future, right? Just evolves like 1 over a cubed. Just evolves with a Hubble dilution. So I simply want to know, given this result, how does this number relate to this cross-section and the mass of the dark matter in a way, or I can turn it around the other way. I can say, if I want this to give me the correct late time abundance of dark matter, what does that tell me about the cross-section? Okay, so how can we parameterize the right late time abundance of dark matter? So the correct late time abundance of dark, well, we know that most of the matter in the universe is dark matter. So we can say that at the temperature of matter radiation equality, it should be true that the density of dark matter is approximately equal to the density of radiation. Now the density of the radiation bath, temperature of matter radiation equality, we know how to do this. This is just of order the temperature of matter radiation equality cubed. The density of dark matter, on the other hand, well, it's the mass of the dark matter times its number density. And its number density, if matter radiation equality happens after freeze out, is just given by its number density at freeze out times the appropriate scaling with the scale length of the universe. So, assuming that the temperature of matter radiation equality is less than the temperature at freeze out, then the number density of the dark matter at the temperature of matter radiation equality is just going to be the number density of the dark matter at freeze out times, let me see if I can do this right, so times the temperature of matter radiation equality divided by the temperature of freeze out cubed. Again, I'm ignoring changes in the number of degrees of freedom. That does make a difference in this calculation, but it's a fairly small difference. And furthermore, we're assuming that T freezes. So furthermore, we're going to assume that T freeze out is approximately the mass of the dark matter. So then that tells us that this equation approximately becomes, this is rho dm. So NDM inequality so this I have messed something up because the energy density of radiation, how does it scale with temperature? Thank you. Okay. Okay. So now we have this result. So this tells us that we can write the number density of dark matter at freeze out to get the right relic density, as we're going to set T freeze out. This is approximately equal to the mass of the dark matter. So then the number density of dark matter at freeze out just becomes the temperature at matter radiation equality times MdM squared. So that describes what you need to get the correct relic density. So now let's go back and plug this in to this equation. So during radiation domination, H goes like the square root of the density of the universe. So H is approximately T squared over M Planck. That means H at freeze out is approximately the dark matter mass squared over M Planck. So when we go back to this equation, and that bell is my cue, but that's fine, we're nearly at the end of this. So we take this result, we go back to this equation. What this gets us so if we put in the factors of MdM, work it out, this tells us that the required cross-section that you need to get the dark matter relic density correct is just given by this result. So in particular, for the familiar case of two-body annihilation, which is the case that many of you have probably seen before, this tells us that this cross-section should be given roughly by, so that tells us that, so the cross-section is just 1 over the temperature at matter radiation equality times M Planck, and it has no strong dependence on the dark matter mass. Now this is only true for the two-body case. For any other case, like three-body and higher cases, there will be a substantial dependence in the dark matter mass for what kind of cross-section like this you need to get. So what does this correspond to? Well, T at matter radiation equality is about 1 eV, so about 10 to the minus 9 GeV. The Planck mass is 10 to the 19 GeV. So you put this together, this is about 1 over 100 TeV squared. So that tells us that if we want this process to work with two-body annihilation, then the natural mass scale, if we say that for two-body annihilation cross-section, the cross-section is of order some coupling. This doesn't have to be the fine structure constant, it's just some coupling divided by some mass scale squared. Then this tells us that for alpha d around 1. This would lead to a mass scale around 100 TeV. This is the unitarity bound on thermal dark matter. This is the statement if your mass scale for thermal dark matter is much higher than 100 TeV. I'm cheating a little here because I've dropped a lot of order 1 factors, but the real unitarity bound for two-body annihilation thermorelic dark matter is actually about 200 TeV, which is better than this approximation has any right to be. So this tells us if your mass is higher than about 100 TeV for thermorelic dark matter, you won't get that kind of cross-section with just perturbative processes. If your alpha dark was, say, smaller, like the electroweak value, this would push you to a mass scale around a TeV. This is the WIMP miracle. So this is the statement that the cross-section that you need to get the right abundance to have an epoch of matter radiation equality of about 1 eV in the present day corresponds to roughly weak scale masses and roughly weak scale couplings. But the statement that is independent of any particle physics model is this one over here. Now, if we wanted to look at this for say higher body annihilation, you can do the same exercise. So say we wanted to look at this for 3-body annihilation. In that case, the sort of general picture for tree level annihilation is that this goes like some mass scale to the 5. It's higher order term here. If you go through this, work it out. So now, so for the 3-body, well, actually, let me just do it for general m-body. So if you plug this result, if you say that it's a tree level annihilation with some perturbative coupling, and you plug that into this result here, then what you end up with is that the mass scale, and you assume that this is the dark matter mass scale, then you assume that then you find that the dark matter mass is again just given by the ratio of the mass to the coupling is given by a geometric mean of the temperature of matter radiation equality times the Planck mass, but now you have extra factors of the temperature of matter radiation equality in there. And what that gives you is that, so for example, for 3-body annihilation, you find that the mass that works is less than about the GeV scale. For n equals 4, if this dominates the freeze out, you would need mass less than about the 10 MeV scale. Again, these less than symbols are gotten by just taking alpha equal to 1 and just taking the appropriate geometric mean of the Planck mass and TAC. So this calculation, so annihilation can, we've just seen for 2-body annihilation with weak scale masses, can pretty naturally give you the correct relic abundance. So since I'm sure everyone is desperate for coffee at this stage, I'm going to wrap up there. But so next time what I'll talk about is, once you have this kind of cross-section in hand, and like it's not directly tied to the weak scale, it's just coming from this number. It can occur in lots of other models as well. Then there are a host of implications for what kind of signals you might see in indirect detection throughout the early universe and in present day galactic halos. So next time we'll talk about that, and then we'll do the methodology of how to work out these constraints in a bit more detail than the first little example that we did at the start of the lecture. Are there any questions before we head off for coffee? Okay.